So today we are going to finish the different sorting algorithms. We also talk about how the sorting algorithm can be done in linear time. Okay, if it's not comparison based. Okay, and today we are going to finish up this whole all these topics, okay, by, the last topic, okay, is called order statistics. This is supposed to be the chapter right after the quicksort, okay. I know we talked about a quicksort probably two weeks ago, yeah, but I hope you guys still remember, okay. The quicksort, basically you have a partition, right? Random partition, and then you keep doing that, okay? That's the basic idea about the quicksort, okay? And so what is order statistics? Sorry. Before I continue the lecture, few things to talk about, okay? First, okay, the third homework will be posted, okay, tonight, okay, along with the sample midterm, okay, sample midterm. Okay, we have a midterm which will be next week. We will not have class next week, okay. Originally, I thought we have, but some students send me email, reminding me on the school calendar. Okay, next Wednesday is actually the beginning of a spring break. Okay, I checked it out, and yes, okay, next week. There's no class, but I still need to come to the school because 就是不用上课啦，但不用上课，但要上班啦。Okay, so yeah, so in case if you have any question, you want to come to school, I'm here anyway. Okay, it's just yeah. So because of because next Wednesday has no class, so. Yeah, we have to follow the school schedule. So yeah, we don't have class next week. Okay, so the week after next, okay, which will be which date? I believe that's the second week of the April, right? April. Let me check. April 8th. Okay. Sorry, April 9th. April 9th. Okay, it will be our midterm. Okay. And my undergraduate here also want me to remind you, okay? We have the midterm on April 9th. Okay, 就是4月9号期中考嘛。The week after the midterm, okay, the week after the midterm, the Tuesday after the midterm to be exact. So it's April 15th. There will be programming exam, okay, programming exam, okay. 所以你们有一个是那个就是用笔写的考试，一个是。上机考。那考试用笔的那个考试的话，笔试的话是4月9号，上机考的话是4月15号早上10点钟。Okay, and what should I say? The TA also want me to remind you, okay, to register. Where is it? I think. think I need to. Register. No, not this one. This one. Oops, sorry. It's not showing. Okay. Huh? Where's my web page? This one. Yeah, this one. Yeah, I'm sorry. I have too many pages open up. I think the TA want to remind you to register a Don't Judge account, okay? Because this is the system that will be used to conduct the programming exam, okay? So you have to register before the programming exam, okay? This is very, very important, okay? I know some students ask about like, if we could like, provide like a syntax for the like a programming language. Yeah, that's unfortunately not possible, okay, because the exam is not open book, okay, it's not open book. So it's we couldn't figure out a way that is not open book, but you guys can check the syntax, okay? It's going to be complicated, okay? So unfortunately, no, okay? But you could use like the programming language of your liking, okay? As I said at the beginning of this class, it could be C, C++, Java, Python, okay? I think like if you could use like the language of your liking, okay, which you are supposed to be familiar with, okay? You are not like a freshman, okay? You are not junior, okay? You are senior, at least you're not sophomore, okay? You are junior, okay? You are at least 30 years into the computer science program. So I suppose like you are familiar with like the syntax of one programming language, okay? So that's like something I want you guys to, to know, okay? Moving forward, okay? So let me recap, okay? We have like a midterm 2 weeks from now. and a programming exam, okay, the Tuesday after the our midterm, okay, and we will have I will post like homework 3 and the sample midterm, okay, to the EE class today, okay, and there's no class next week, okay, and there are some like regulations that you should know, okay, such as to register for Don't Judge, okay, and also remember, like if you are not familiar, okay, at this point, if you are not familiar with your programming language, okay, it's a good idea, okay, you can, you know, refresh your memory, okay, before going to take the programming exam, okay? Okay, back to the lecture, okay, the order statistics, okay? So what is order statistics? The order statistics, oh, I think we talked about this last time, right? Yeah. So order statistics basically just means like you are given some numbers. Of course, these numbers are not sorted. And you are asked to find the ith rank number from these numbers, okay? Of course, to make our discussion easy, okay, you could assume these numbers are not are distinct. They are different. Okay, all the numbers are different. Okay, so you could imagine. Okay, if you do, you know, in some particular special case. Okay, you know, if the first rank will be the minimum number, the nth rank, if you have n numbers, then it will be the maximum number. If it's like a middle rank, it will be the median. And a very direct approach is just to solve these numbers, and then you just find like whatever rank you want. Obviously, this approach take like n log n. Okay, you can use either merge sort or heap sort. Okay, but obviously we don't like it. We think it's not good enough. Okay, so what do we do? Okay, so the idea is like this. Remember, in the quicksort, okay, there's a partition, right? That partition allows us to break your numbers into two groups, okay? You know, the first group contains the number smaller than the pivot. The second group contains the numbers that are bigger than the pivot. And pivot, of course, I mean, at the end, sit in between, right? Okay. Yeah, I mean, 有时候我看你们的脸，我都不知道你们懂不懂我的英文，希望你们懂啦。Okay. Anyway, okay. So the idea, okay, is that, okay, if we could use that partition, okay, if we could use that partition, okay, to help us achieve finding the ith rank number, it will be a good idea, okay? So this is rank select, okay? In this rank select, okay, we have an array A, we have a P, have Q, and I. Basically, P and the Q stands for the two ends of the index that you are considering in the array. Okay, 就是你那个 array 你有个起始点的 index 跟那个终点的 index。那当然开始 at the beginning, okay, I will be P will be 1, Q will be n, right? Okay, but you know, like because this you know, rank select, I mean, obviously is going to be called recursively, so we need to, make sure it works for like a different, part of the array. So we specify like P and Q as the, lowest index and the toppest index, okay, of the array that you are considering, okay. And I would be the ith rank, So here we want to find the ith smallest, okay, from A, P to Q, okay, in this range, okay. So obviously, if P equal to Q, what does that mean? If P equal to Q, that means we only have one number, right? You only have one number. Then return AP, because, well, if you have only one number, okay, it is the smallest, it is the biggest, it is, well, pretty much like whatever rank you consider it is that number, right? So you just return AP. Okay, otherwise, you call the random partition, okay, APQ. So try to partition this part of array in random. Okay, you remember like we discussed about the random partition. Okay, basically we just first like generate a random number, okay, in the range of P and the Q, okay, in the range of P and Q, and then do a swap to make that, number the pivot. Okay, basically we just want to make sure like the pivot is not going to be necessary to be like the first number. Okay, because we just want to randomize the partition, and then we do the we do the partition as usual. Okay, just like what should I say? Like in a quick sort. Okay, so at the end, okay, it's going to look like this, right? Okay, the index R will hold your pivot. Okay, and all the number in the front, okay, we don't know the order, okay, the rank, okay, I mean, of course they are still not sorted, but we know like these numbers will be smaller than your pivot, which is marked by yellow, right? And all the numbers here, okay, with the index larger than R, okay, will be greater than the pivot, okay. Again, they are not sorted, but we know like, this part, they are smaller than pivot. This part, they are larger than pivot, okay. That's the result of your rand partition, right? And you are going to return the index of the pivot, which is R, back to here. So that's the index of the pivot, okay? And then you try to see like, R, okay, I mean, R minus P plus 1, okay? There will be, the rank of AR, because, well, this is the index, right? But the P is not starting from 1, right? So say like P start from 5, and this is index 10. Then it's going to hold like a 10 minus 5 plus 1, the 6th largest number, in here. So so it's like a R minus P plus 1. Okay, so that's like that indicate the rank of your pivot in this range. Okay, in this index range. Okay, and then you try to compare this rank with your with your K. I'm sorry. With your I. Yeah, with your I. So if I equal to K, obviously, like we have we hit the jackpot. Okay, we found the right number So we just return the pivot. Okay, if I is smaller than k, that means the index, the rank, okay, you want to find that number is somewhere here. Okay, if that's the case, okay, you recursively call rand select a, p, and this is r minus 1, and then it's I. Okay, you try to find the i's rank number in the range of, in the index range, from between p and r minus 1. Okay, otherwise, else, okay, you return, okay, you are going to find that rank somewhere here. Okay, if that's the case, obviously the range will be, it's still the array A, the range of the index will be r plus 1 to q, but the rank will be I minus k, because you already, these numbers are already, are smaller than the rank. So you need to say, if you want to find 15th largest number. So if you already have 10 numbers here, so it means here you want to find the 5th largest number, right? So you need to, your 15 need to subtract that 10. Okay, so that's the basic idea. So this rand select, okay, obviously it's a recursive call, and it make use of the random partition that you have learned from quicksort to do the trick. Okay, so how good is it? This is, let's have a look at the example. Okay, so we are trying to find the 7th smallest number from this, and assume the first number is the pivot. Okay, obviously you need to randomize it. Okay, but let's just assume after the randomization, okay, we use the 6 as a pivot. So you, if you still remember, what happens is that, you have two pointer, okay, 1 point to 10, okay, 1 point to, if it's 10 is bigger than 6, you keep going, and the 13, and now it's 5, okay, then you swap 10 with 5, make sure so 5 stay here, and you have 13 and 10. So then that number move to here, and then 13, 10, keep going, 8 is greater than 6. Okay, keep going, 3 is not greater than 6. So you again swap 13 with 3. So it becomes a 5, 3, 5, 3. And then 13, 8, 10, 8, 13. Okay, and then 2, you need to do a swap again, because 2 is smaller than 6. And then 11. So, and when you are done, you need to do a swap. Okay, and that's when you get this array. That's after you finish your random partition. And now the 6 is here. And this part holds the number smaller than 6. This part holds the number larger than 6. And because we are trying to find the 7th smallest number, and here, we are returning the index here. Okay, the index here is 4, right? It's 4. So obviously 4 is smaller than 7. So the number you are trying to find is here. And we know not only the number you are trying to find is here, but also, okay, you want to find the 3rd largest number in here, because 7 minus 4. You want to find the 3rd largest number in here. So you continue doing the random partition, and recursively. Okay. So I think like the basic idea is very straightforward, right? It's very straightforward. And this random partition, okay, to be honest, in most cases, it performed very well. In most cases, actually, like it's just like a quick sort, okay? It practically is the fastest algorithm for the order statistics, okay, to find like any any rank, okay, number from a bunch of unranked numbers, okay. But how about like complexity? Okay, so if we are lucky, okay, say every time, okay, every time we are able to partition the numbers, okay, into like the ratio 1 to 9. This partition, this random partition is, well, actually we probably should already call it like unlucky. But if we can guarantee such a ratio, okay, and let's assume the worst, okay, every time like the partition, okay, I mean result in like two group with a ratio of 1 to 9, and every time, unfortunately, the rank, the number you are trying to find is in the larger group. Okay, that's a kind of worst case, right? But still, we are still lucky because like we are able to. I mean, every time this partition, I mean, guarantees certain ratio. Okay, so we are able to cut the size of the problem, okay, by a constant ratio. Okay, well, 1/10 actually. Okay, so if we are able to do that, and obviously you also need to take into account of the random partition, which is linear, okay, which take linear time. And this one, okay, if you use like a master theorem, it's going to easily tell you that it's like it's going to be linear, okay, because like n to a power of log, 10/9 base 1, okay, this one is going to be n to the power of 0, so it's 1. So this order dominates. Okay, so according to like a master theorem, okay, the order is linear. So linear, okay, remember like previously, the naive approach, we sort these numbers and then try to find the index I, okay, for your order statistics. This one takes n log n, right? So the linear complexity looks nice. But if you are unlucky, say every time, okay, your random partition end up with like only like getting rid of one number. Is that possible? Yes, that's possible, but that's really, really bad. Okay, you are really, really unlucky. So it's going to be Tn equal to Tn minus 1 plus theta n. It basically every time you are only able to get rid of one number, which is, by the way, which is the pivot. Okay, in other words, the pivot you are getting is either the largest number or the smallest number. As I said, is it possible? Not likely, but yeah, I mean, there's like a small chance this may happen. Okay, if this is the case, you can use like a substitution method to easily derive. It's like let's just assume that's n, okay? There'll be Tn minus 2 and the plus n minus 1 plus n. So you get this one. From here, from this one, you get this one. So continue doing so until you get T1 plus 2 plus 3 plus dot 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 plus n. And this one, you can assume that's 1. So it's going to be like a very simple series. And your elementary school math tells you that's n squared, right? So n squared, okay, well, that's pretty bad, right? That's worse than the naive approach, okay, which you sort the numbers and then, find the I smallest one, like by going to the index I. I mean, so this, of course, this is really, really unlucky, really, really unlucky. It's like every time you are only able to get rid of like one pivot. Okay. But in reality, okay, I need to keep reminding you, this is just like a quick sort. Quick sort, the worst case complexity is n squared. Okay. But in reality, like it is like if you have like a large number of unsorted numbers to sort, quick sort is usually, okay, if you don't know anything better, quick sort is usually the best like comparison based sorting algorithm out there. Okay, so this random select, this algorithm, okay, similarly, okay, it is actually the fastest like Euler statistics algorithm, okay, in practice, okay, but the worst case it could be very bad. So can we analyze it? What is the average case for this algorithm? Okay, so here we go. So of course, like this is obviously a randomized algorithm, right? So in the randomized algorithm, remember I told you guys, like in the randomized algorithm, okay, we are looking at the expected time complexity or average time complexity, right? Okay. So basically that T of n denote the random variable for the running time of rand select on the input of size n. Okay. So let's assume all these random numbers are independent, okay? And then we define an indicator random variable. This xk, okay, equal to 1 if partition generates a k to m minus k plus 1. Minus 1. So it's like we are able to at least get rid of a pivot, right? So k and the n minus k minus 1, so these two groups. Okay, so this is like if this is the case, xk is 1. Otherwise, okay, it's 0. What does that mean? It's otherwise. It means like okay, your partition generates obviously your partition always generate your random partition always generate a partition. That's for sure. But it's just like your partition split. The split is not k to n minus k minus 1. Okay, in that case, like your index, is 0. Xk is 0. So with that, now we want to find, okay, the upper bound, okay, or average case. Okay, let's do this. Okay, assuming, okay, we are trying to examine all the possible cases. Okay, so the first case is that t of n equal to, the first case is t max 0 n minus 1 plus theta n. Okay, so why do we use max? Because we try to, again, like consider like the worst case. Because when you partition two groups, okay, the worst case is like the number you are looking for is in the larger group, right? Okay, if the number is in the smaller group, then you're lucky. The time to find that number will be reduced, right? So let's just assume like every time after the partition, the number always sits in the larger group. Okay, so that's why. Okay, you know, we have a max 0 n minus 1 plus theta n. Okay, this is 0 n minus 1 split. Okay, and the second one is, I mean, we split it into 1 and n minus 2. And again, the number is unfortunately in this larger group. Okay, and this linear time is always like that. And the blah, 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 blah. Okay, so there are all possible cases, right? So t max n minus 1 0 plus theta n. Okay, if the split is 0, n minus 1 0. Okay, and we assume all these are equally likely. And obviously, only one of them is possible, right? Only one of them is possible. Okay, because we are talking about different splits, right? So once you have a pivot, the split is set, right? I mean, it's going to be certain split. Okay, it's one of these splits. Okay, so it's like you can use the xk, this indicator. Okay, here. Okay, in your formula to write the whole thing into one single formula like this. So k starts from 0 to n minus 1 xk t max k n minus k minus 1 plus a linear time. Is it good? 这个还可以吧 ？OK， 我们就是用那个 xk 把它写下来。Remember, there's only one such xk to be 1. All the other xk's will be 0, depending on, you know, the choice of pivot. Okay, so yeah, I mean, it's going to be one of these. 对不对？你就只有一个会成立嘛，但你不知道是哪一个，所以你就用这个 xk 来写，因为 xk 它只会有一个是1，其他都是0。So if you agree with this, then, okay, because we want to find the average case, so we are applying the expectation. So we try to apply the E, okay, to the T of n. So because T of n is written like this, so it's going to be like this. So we can take, because basically we are taking expectations on both sides. And then, okay, you know, like, you know, because of linearity of expectation, you can put the E inside this, you know, the summation. Okay? So it's going to be something like this. And then, okay, this part, you apply E on this part, you apply E on the other part. Okay? of course, you also apply E on xk. So times blah, 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 blah. So because xk is independent from other random choices. So, and because of that, you know that exk, okay, will be 1 over n. So this thing will be 1 over n. And because it is 1 over n, you can put it here. And you apply E in this term and this term separately. So 1 over n here, 1 over n here. And then, okay, if you write this, because we're talking about the max k n minus k minus 1. Okay, if you write it, okay, k from 0 to n minus 1, if you really write it, you will find that you actually write, the index from n minus 2, n divided by 2, okay, this roughly n divided by 2 to n minus 1, you roughly write like every term twice. Okay, so you can write like this one and get that 2 out here. And this one, this term, okay, basically, okay, you see, this part, this linear is independent of k, right? So k start from 0 to n minus 1. So it's basically you add this theta n times. So this is n times theta n, but you divide n here. So it's going to remain to be theta n from here. So we have this. So far so good, right? And then there's a trick we can play. Okay, there's a trick we could play. Because this is like, this is something that you don't know how to, continue at this moment. Okay, it's but this thing is not as bad as the quicksort analysis. Remember, in the quicksort analysis, we try to use inequality in the analysis. Okay, and I told you guys, okay, that inequality will be used as a one homework assignment. Remember that? And I did ask you that question in the homework assignment, right? Okay. So similarly, okay. Now what we want to prove is that, okay, this thing is actually, going to be linear. Okay, so it's this E of like a T of n is going to be small or equal to Cn for a constant C greater than 0. Okay, so so how do we do? Okay, we still need a help from an inequality. Okay, so first, okay, we need to make sure that in the base case, okay, this C is chosen big enough so that like for the base case, like this thing holds. Okay, and then here comes the inequality. Okay, this thing we have like k from n divided by 2 to n minus k. K is going to be small or equal to 3 over 8, okay, times n squared. Again, I will give this one, okay, I will assign this as a homework question for you. Okay, remember, like we have like a homework assignment which will be given to you tonight, right? So this is like one of the problems that you are going to consider in your homework assignment, okay? But anyway, let's assume you have this. Then, okay, we could use like, we could consider, because here we want to prove this, right? So we can use like a induction hypothesis, okay? So this term will become, okay, originally is a ETK, now it becomes a CK. This is because the induction, okay, induction hypothesis, and C can be obviously moved to the outside. C can be moved to outside, okay, and then we have this one, exactly this one, okay. So we could replace that, summation k to be 3/a times n squared.